This week we're going to look at models which include level 1 predictors. So we've talked a lot about level 2 predictors and taken a look at how they compare to the unconditional model. But when we start involving level 1 predictors, things get a lot more complicated. So let's start out by looking at a model with a level 1 predictor and compare it to the same unconditional model we've been looking at throughout the semester without any predictors. So just to verify, we're going to use the variable sleep, and we see that sleep varies within clusters, so each of these observations is the same person, and here we see sleep has a different reading, as does our outcome variable, positive affect. So what do we think is going to happen in our model to our variance parameters, sigma squared mu and sigma squared epsilon, now that we've included a level 1 predictor? So we take a look, and we see that the level 2 variance has dropped a bit from 1.79 to 1.72, but the level 1 variance has changed very little. And so why didn't our level 1 variance change more now that we've added a level 1 predictor? In fact, this change is so small it could just be a rounding error in the algorithm somewhere. Let's look at another example of a level 1 predictor. So here we're going to use negative affect, and as you can imagine, negative affect and positive affect are fairly strongly correlated. And so here at the top, we have our same unconditional model again, just no predictors, same as on the last slide. And here we have the model with negative affect instead of sleep. And here we see that our level 1 variance has changed quite a bit, as has our level 2 variance. So why do we think the level 1 variance changed more with this predictor than with the previous predictor? The answer is that level 1 variables vary at both level 1 and level 2. And not only that, but they can have totally different effects at each of the different levels. This is called a contextual effect, and it's also known as the ecological fallacy. The ecological fallacy happens when we try to make inferences about individuals based on patterns related to group membership. A particularly famous type of ecological fallacy is known as Simpson's paradox, and this occurs when we try to make inferences about patterns among individuals when comparing groups of different sizes. This isn't the only type of ecological fallacy or contextual effect, but it is a famous example that we'll take a look at here. So here what we see is the UC Berkeley example, and this was a fairly famous study that was done in 1973, where they looked at the admissions rates to UC Berkeley grad school based on gender, and they found that men were admitted at a much higher rate than women, which isn't necessarily a surprising result. In 1973, we would sort of expect there to be gender bias in graduate school admissions rates. What was a bit more surprising was when they actually broke it down by department, they found very little gender bias. And this surprised me as well. I mean, you would think, I would definitely think there would have expected there to be legitimate gender bias in the grad school in 1973. But here we see the top 6 departments here, and what we see is the actual admissions rates by gender for each department are fairly similar. In fact, this first department, the largest department, had a higher admissions rate for women than for men, as did the second department here, slightly higher. A few departments had higher admissions rates for men than women, but the differences were fairly small. So what's going on here? Why did we have this different directional effect when we look at the aggregate than when we look at things department by department? And the answer, it turns out, is that there were differential application rates for different departments by men and women. So men tended to apply to departments that had much higher admissions rates, and women tended to apply to departments that had lower admissions rates. So what we see here at the top, this large department, it has a fairly high admissions rate for both men and women, but we see that lots of men applied and not that many women applied to this department. Whereas we look at this department on the bottom, it has an extremely low admission rate for both men and women, only 6 and 7%, but we see a pretty balanced number of men and women applying for application into this department. If we look at the one above it, we see a sort of similar thing. Another fairly low admissions rate. It's in the below 30%. But we see actually twice as many women as men applying for this department. So women were tending to apply to these ultra-competitive departments, while men were tending to apply to these less competitive departments. And that's why we see this difference in the overall aggregate. And this isn't the only type of contextual effect or ecological fallacy, but it is a sort of famous one that I want to highlight. So a good way to identify whether we have contextual effects in our data is to visualize it. So we can plot both the within group effects and the between group effects. And this is sort of one heuristic way to do it. There are probably other ways to do it. This isn't necessarily a perfect way of totally quantifying a contextual effect, but it is a way of visualizing if one is present in your data. And that's to separate out the cluster means of your two variables and compare them to the average within group regression intercepts and slopes of your groups on the two variables. So here we're going to start just by taking the average within cluster for both positive affect and sleep. So we're using this aggregate function that we looked at back in when we were sort of first going over R. I think this was in the second lab. And we're going to look at both P affect and sleep. The cbind function here is saying we want both of them. And we're going to say we want the mean at the person ID level. And that gives us this table here where we have the mean of positive affect and sleep for each cluster, or in this case, person ID. So the next thing we want to do is we want to get a unique regression for each cluster across each observation for each cluster in our data. So to do this, we're going to use the Plyr, P-L-Y-R package. And just a quick warning, if you're going to do this, make sure you use Plyr. If you're going to load both Plyr and dplyr, dplyr is sort of a more modern version of Plyr, make sure you load Plyr first. So Plyr isn't overwriting dplyr, but dplyr overwrites what it needs to in Plyr. dplyr has some different methods for doing what we're going to look at here today that some people would really say are much better. They're a little bit confusing to my brain, so I like to use the old school Plyr way. I encourage you to take a look at what dplyr has to offer if you're interested in getting more into R programming, though, because it's sort of a more modern way of doing things that's a little bit beyond the scope of this class. So I'm going to load up Plyr here, and then this dlply function, what it's going to do is it's going to repeatedly perform some function on our data by some factor. And in this case, we want to perform a regression of sleep on P affect for each person in our data. And so what this is going to do is it's just going to return a list object that has the regression for each person. And then we need to take that list and turn it into a table. And we can do that with this ldply function. So this is going to extract the coefficients from this list mod.cl. And what this is going to give us is an intercept and a slope for sleep for each person. So this is just a regression of sleep on P affect for each person with an intercept and a slope. And we can already see the slope for sleep is a little bit variable here, which we'll get into more in a bit. So the next thing we want to do is just take the average of the within cluster slopes and intercepts. So here I'm just going to save this, the average of all the slopes, as a variable called slope, or just an object called slope. And here I'm going to take the average of all the intercepts and save it as intercept. And then before we start plotting, one more tip. You might want to take a look at the Papaja package. So this is a package that's also in development, although it's been around for quite a while now, a few years. And it does some really great auto formatting of things like figures and tables. We're just going to use it to make our figures look our plots look a little prettier here, but you can do some great things with table formatting with it as well, where it automatically formats your R tables at the APA format. So again, it's still in development. You have to install it from GitHub. Here's a link to the installation instructions if you're interested. But for our purposes, it just adds something to our ggplot here at the end, and we'll take a look and see what it does at the end. So what we're going to do now is plot our results one step at a time. And so you can do this in ggplot, where everything you can start with sort of this initial command where you're just creating the skeleton of your plot. So we haven't added anything to this. We're just creating an x and a y axis with a blank plot, and then we're going to iteratively add to it with pluses. So now what I'm going to do is I'm going to add on top of this the points for our level 1 observations. So this is just all of the observations of sleep and P affect in our data. And I'm just going to specify, give them a unique shape and a unique color and a unique size, because I want to be able to differentiate them from the level 2 observations. So here we get all of our observations. This is all of sleep and all of p affect, ungrouped. It's just every single observation with no special grouping to it. So then the next thing I'm going to do is I'm going to add on top of that the cluster means for sleep and p affect. And I'm going to give these points a slightly different shape and color. So I'm going to say these get, this shape that's 20, this color that's black. So this is just saying I want something a little bit different so I can differentiate them. And so we see now these pop up and these sort of like diamond shapes. And we can already see the pattern's quite different than it is in our X's, which are the level 1 observations. So now, just to clarify that a little bit, I'm going to add some lines. So the first thing I'm going to do is add the average intercept and average slope of each within person regression. And we can do this with the geom AB line function. So what this does is just plots a line based on an intercept and a slope. And so I remember, if you remember before, I saved the average intercept and average slope as something called intercept and slope. So I can just fill those in here. And I'm going to make this line red. And so this is going to give me a line with this intercept and this slope. And you can see it's a pretty flat line, sort of matches what we're seeing in the X's here a little bit. And so now finally, the last thing I'm going to add that's not simply aesthetic is the regression line for the cluster means. So now I'm going back to my cluster mean data. And to get a regression for any data set, or a regression line for any data set, you can use this function called gmsmooth with method equals lm, and that will simply add a regression line between your two variables, and I'm going to make se false, otherwise that would give us an error band or something like that if we specify this to be something else. I'm going to make my line blue. And so now we get our cluster mean regression, and we can see it's a totally different line than the red line, which is our average of our level 1 slopes and intercepts. And then finally, I'm going to add a few aesthetic tweaks to my plot just to make it look nice. I'm going to set the scale of the x-axis and y-axis so it has the right limits and number breaks. I'm going to label them so they have the right they have proper labels. And then this theme APA is the thing that came from Papaja, and it's just going to make the lines in the background look right. And so here's what we have. This is our final plot, and this is pretty much what you saw in lecture.